in continuation with whatever we stopped in the previous session, so we'll do that. So if I come back, as I told, I think I'll get rid of this. I hope I can, you can hear me, right? So one of you can unmute and tell, is it fine?
Yes, sir. We are here.
Okay, yeah, thank you, thank you. Okay, so as I showed in the previous session, we did one example for Fe2O3. So Fe2O3, they have three samples here. So if I go back here, there is one with the bulk. Bulk means, as I told, it is at 12,200. It is heated at 1,200. And then there is one which is heated at 750. Okay, slightly lesser temperature. So the red one is at 750, blue one is at 1,200. Okay, and if you see already here, so there is small difference in your peak shape. Okay, so if I then there is one more third one which is actually very low temperature. So this one is nano, which is quite low temperature. Okay, and if you see the peak width of this nano, it is quite large. So if I want to compare all these three, and you can see there is a difference in intensity. So what I can do is I want to bring it normalize. So you can do it from here. Okay, you go to calculations, normalize, then you put some value. So this is already around 7,000. So I'll keep all the things to 7,000. That means all the peaks should be coming to 7,000 in the sense the main peak. Okay, not the other peak. Other peak will be they will be normalized to that particular value. Okay, so this is the highest peak, so I am asking this peak to be 7,000. So this peak has to come to 7,000, and then correspondingly this peak will come to somewhere here. Okay, so it is normalized like that. Okay, so I think it's fine. So now if I see this, you can see this is a bulk sample which is 1,200. So it is having sharper peaks, and you can see already they are having a similar your K-alpha and alpha 2 is quite distinguishable. Okay, but when you go to the slightly lower temperature like 750 degree, this is already micron size, but still it is not very good crystalline. Okay, so you can see these peaks are still not very well distinguishable. You can distinguish, maybe there is a peak here, but it's not better distinguishable. And if you go for nano, you can see it looks like as if it is a single peak. Okay, all the data are collected for the same time and same on the same machine on the same thing. Okay, and if you go to higher 2 theta, you can clearly see that difference. Okay, so this 1,200 degree sample is well distinguishable. Okay, with the peaks, and then these things are slightly not that good. Okay, so these are the things. So now what I will do is, we have done profile matching for your bulk. So I showed that for bulk. So this is a profile match for bulk, and then we did also a profile match for nano. Okay, right? So so if I go here, so for nano we have done the profile matching. So now what I will do is, we can use these data for finding the Rietveld refinement and so on. Okay, so sorry, for finding the crystalline data and also. Okay, so now before that I will just have this small thing, or till I think, I don't know how many people are there. So 22. Okay, so I think for next 5 minutes I will just try to uh, do one more profile for the intermediate sample. Okay, so for this again, you don't have to do again all the things. So what I will do is, I will take the PCR for bulk, and then I will copy this PCR, into a new folder, and I'll call this as 750C, okay, data, and then I will paste it here, okay. So in this case, in that way, I don't have to repeat all the things, okay. So I'll just put FA203 750 or something, okay. So now I can just open that PCR directly, and I can try to do the whatever changes I want to do, okay. So I will open this. So we will do in the same EDPCR. Maybe let me not confuse you with this. So I will open the EDPCR. So 750. So I'm going to take this. So I have to change. So pattern is the same. I have to change the file name. So I'm going to go here, browse the file name. So actually, this is your next sample. So I'll just copy it into this folder. Okay. So I'm going to open that. Then I will make sure, okay, it is a copper radiation. Then it is good plate shape function. So then background we will change it later. So I will keep it like that. Then I have to also go to phases, and then I need to change the contribution. Okay, so this is still a profile matching. I don't want to do Rietveld. So I have to change here. This reflection has to be automatic. Okay, for the first time. Whenever you run first time, it should be automatically generated from the space group. If not, you will get the error. Okay, so this is one thing you need to take care. So symmetry is fine. So rest is fine. So before I can run the program, I need to just have a background. Okay, so for that I will open that file, uh, 750 file, and then I'm going to take the background. Okay, so select background point. So I'll just do this. So you try to take as many points, data points as you can, and then you can save it. Okay, so I have taken some points, and then I'm going to save it, save background. Okay, it's inside the 750. So I have 19 points, fine. Then what I can do is I can go here in the refinement, and I can import those things. Okay, so import the data points, which is here 19 data points. Okay, so it is fine. So right now it is ready to run. So make sure we have 0 is running. Even your ABC is checked. Okay, so this need to be checked. They are running. Then what I do is for just clarification, I am going to also open it here. Okay, so this is a PCR file. So sometimes this is not going to change. This you need to take care sometimes. Okay, I'll close this again, open it. Then this has to be 1 1. Then this has to be also changed during the run. Okay, so 21 21 and then 31 and 21. Okay, so this I'm now changing this, and then what I will do is I'll save it, and I can open the save here. I will run it. Okay, so now if I run it, then it has to do the fitting. Okay, so let us see. Okay, so it is done. So let us see what it has done. Okay, so if you see, it is we have done here all the things. Okay, so there is some problem here. Okay, I'll put this as auto again on. then I will try to run from here only, because sometimes this we edit PCR gives some error. It is changing that AUT to 0. Okay, so that is why I'm again repeating it. So you can see the peaks are shifting to the regular one. So there is this difference here in the peak position. Okay, so you can run it somewhat one or two more times, or what you can do is you can change this x-axis into D. Okay, so if I change it to D, then this will give values in D. I can check this is 110. So as our uh, this is R minus 3C space group. So 1 means A and B is equal to A is equal to B. So with respect to this peak, actually we can calculate the values. Okay, so how to do that I will show you. 2.5152, you multiply this by 2 times. Okay, if you multiply that by 2 times, then you will get this value. Okay, so same way, but this is the calculated value for red, sorry, for the black. I want to shift this to here. So what I need to do is I need to take the proper value. Okay, so you can, if you see here, this value should be 2.5232. Okay, into 2 times it will be. Okay, so okay, so let me change that. So it has to increase a little bit. So from 2.551, it should increase to 2.5235. Okay, into 2. You just do it into 2 times. So it will be 2.5, sorry, 5235 into 2. It should be 5.04 something. Okay, so I just put this as 5.050. Then again this I'll put this as 5.05. Then I will make this reflection to start from beginning. Okay, so if I do this, and then I will save it and I will run the program. Okay, so if I do that, then what happens is it should shift. Okay, you can allow the program to do it, but it will take long time. Okay, so sometimes it will give error. So what I'm doing is I'm just trying to do it manually. Okay, so let me see. Now it should work. Okay, so you can see already it is shifting a little bit, and then yes, now it's working. Okay, so you can see it came to 26. Before it was higher. So now what I will do is I will run one more time, so you can you just try to come back to original position very quickly. Okay, so it is almost good. So now I'll try to run one more time, then I will do the UVW refinement. Okay, so now you can see in the compared to previous time, this is becoming better, because if you don't give really good model, it is your software will struggle to get a good fit. Okay, so that is why you should always check the parameters, whether you are giving proper parameter or not. Okay, so if not, then you need to adjust the parameters manually, then it will be easier to do the refinement. Okay, so now the peak position looks good, so that means ABC are somewhat okay. So then what I will do is I will just try to do the refinement of X and Y. Okay, so this I'll put so the maximum is 3, so now it is 41, and then this is 51. Okay, so I'll try to finish it fast, so then I can complete the other things. Okay, so I think it's okay, 1.81. So just for demonstration, I think it's fine. So you can see here there is some peaks, extra peaks here. Okay, so these are maybe some impurities which are not taken into account. So if I want to just don't want to show this, what I can do is I can have a excluded region. Okay, so I can open the PCR in your EDPCR, and I just want to get. I don't want to do fitting in this range. So what I can do is I will see what is the range. So this is from 27.5 up to 31.95. Okay, so you can have a excluded region. So you go to pattern, you go to excluded region, add one excluded region between 27.5 and then between up to 31.80. That means your program should not do any refinement in this range. Okay, so this is one more example where you can also change the uh, fitting region. Okay, so if you if you don't want to consider some things which are impurities, then you can also do like this. Okay, so that is why I just did this. So these are some of the small things we can learn one by one. So you can see it is not fitting that particular part, it is fitting the rest of the things. Okay, so in this way you can always try to do better fitting. Okay, so you can see now it is the fitting is good. The red is your data, and then black line is the calculated one. So this is quite okay. So I will stop at this point, and then again I will come back here. So before that we will have some very short discussion. So if I open this, so till now what you did is what you learned is you learned how to do a phase quantification. So if it is a single phase, how to get the space group ABC values, and then if it is multi-phase, then how to get the two different phases. Okay, and then you did a ritual refinement to get the crystal structure. Okay, so if you want to know what is the crystal structure, so you have to do a complete ritual refinement. Then you can use a Vesta or your Foolproof Studio, or if your institute is having license for diamond or crystal maker, you can use those things also to draw the crystal structure. So what you need is just a zip file, and this zip file you generate by when you're doing your ritual refinement. Okay, so if I do a ritual refinement, then it will then I can generate the crystallographic information file or zip file. So these are some of the uses of your XRD. Apart from that, so there are some more things what you can do. Okay, with your X-ray diffraction. Okay, so if you have a very good X-ray diffraction data, you can also do some other things. So these are some other things. One is your crystalline size and strain. So we will discuss this in detail. Phase and crystallinity of amorphous sample. So this is normally done for pharmaceutical or organic or polymers. So if you want to know what is the crystallinity of a polymer, you can, depending on your synthesis condition, you can have a different crystallinity of polymer. So for that, you can also get this amount of crystallinity of your polymer by using a X-ray diffraction. Okay, and if you are working on a thin film, you can do lot more things which I cannot cover everything right now. Okay, so some of them are like roughness. If you want to know the roughness of your sample, of your thin film, X-ray is one of the non-destructive technique. So normally you can use EFM, AFM, all those things, but there is a possibility that you are going to uh, destroy your thin films. Okay, so that means as it is a contact method, there is possibility that you are going to destroy the surface of the film. So if you don't want to do that, if you want to have a non-destructive characterization, then you can also do something called as reflectance by using this X-ray, and then you can get this roughness, and also you can get for very rough estimate of the thickness of the film. Okay, and then if you are working on a metals, like if you are working on some intermetallics, and like your stainless steel industry, so if you want to know what is the stress or strain that you can apply on a given material, so that also can be done by using this X-ray diffraction. Okay, so apart from that, one of the most common and very known things which is coming up is your scattering experiment for especially for your nanoparticles. Okay, so if you take any nanoparticles, you can do small angle X-ray scattering, and you can predict the shape of the particles. Okay, instead of doing a TEM and SM, So you can also do that. And one more thing is your pair distribution function. This is mainly for getting more localized atomic information. Okay, so how each atom is distributed, what is the environment of atom. So all these things you can do by doing a PDF, pair distribution function. So this nowadays you can these two SACs and the PDF. Nowadays there are some X-ray machines which you can do even in your lab. Okay, so with a regular X-ray machine, you get a separate attachment where you can get this all this information. Okay, so let us look in a little bit more. So when it comes to peaks, okay, so if you take the broadening of the peak, so there are several contributions. Okay, the first contribution is your instrumental contribution, and then the second one is your sample contribution. Okay, so if you see some of this literature, they give some size, crystallite size. So this crystallite size, how they get? They say they get it by Scherer formula. So this we will discuss again. Okay, in the next slides. And then they will use this formula. Okay, k lambda by width into cos theta. Okay, what is this width? Width is actually your width of the peak. Okay, so they just take this is the peak width. Okay, so but when you take a peak broadening or peak width, it is not just due to sample. Okay, so a lot of times there is contribution about the from the instrument. This we discuss in the first PowerPoint itself, right? So when you have this broadening, peak broadening from instrument, then you are trying to use the same width as a parameter to find some crystallite size. So this is not correct, right? So for that, what you are supposed to do is you have to do some subtraction. For example, if you are having if you are taking your full width half maxima, you should not directly take full width half maxima for your from your sample. Okay, in principle you need to subtract that instrument contribution also. Okay, so if I want to say b sample will be, b means it is the width broadening. Okay, broadening of the peak is due to instrument and also your other things. Okay, so in this case, I will take this one. So if I want to say b sample, the width due to the contribution of sample is b total minus b instrument. Okay, it means you need to get rid of the instrument part. So how to get rid of this instrument part? So for this you need to do some X-ray diffraction like what we did in this case. Okay, so I will just show you again this one. So if I take this, why we did this scan of 3 different sample is, so if I want to know the crystallite size of my nanoparticles, then I need to get rid of the contribution from my instrument. So how to get rid of this is, you have to take some bulk sample with very high crystallinity. So you can see this, if I compare these two, you can see this peak is coming from a bulk sample, which is very highly crystalline. Okay, still there it has some width. Okay, compared to nano it is smaller, but still it is having some width. So this can be even due to the slits which you are using. If I use a smaller slits or narrow slits, then what happens, this peak will become smaller. If you put a bigger slate, then this peak would become bigger. Okay, so this is not exactly only because of sample, it's also because of the instrument. Okay, so that is the meaning of this what we are discussing here. Okay, so now if I want to find the crystallite size, the proper way is you need to do a experiment with a very highly crystalline sample, and then with the same settings, like if you're using some 0.2 with slits, then you need to, for bulk sample, then you need to use the same slits for measuring the nano sample. Okay, only then you can use apply this kind of corrections. Okay, so now then there is also some people also give strain. Okay, strain of the due to nano sample. Okay, so I will show some of the examples. So this strain, if you take, there are different contributions. The first one is, so if you see here, this is the unstrained sample. Like if you take very highly bulk or highly crystalline sample, which is well ordered. Okay, so this is interplane layers, which is like your crystal planes. Okay, so these planes are very well ordered. In that case, what you get a peak at some position. Okay, if you apply some stress, that means in this case it is a compressive stress. That means you just take a material and then you try to uh, apply some uniaxial stress, like your hydraulic press. Okay, so you just put this sample in between hydraulic press and then you press it. Then what happens? These planes are not disturbed, but there is a compression. So this is one kind of strain which is a homogeneous strain. So in that case, what happens is, if we take the peak position, it will be shifted. Okay, so this is for homogeneously strained sample. So for that, what you are supposed to do, you should take X-ray diffraction on unstrained sample, and then you should take X-ray diffraction for strained sample. The next one is, there is a inhomogeneous strain. For example, there is some so you're trying to dope something in between. So this will also induce some strain in the lattice. Okay. So in this case, what happens is, instead of shifting the peak, there will be a broadening of the peak. Okay. So this is what they have shown here. So there can be shifting the peak, at the same time it can be having broadening of the peak. So if there is a broadening of the peak, then it is an inhomogeneous strain which is induced in the system. If it is only just a peak shift, okay, in that case, what happens? The peak will not change. Okay, you will have the same peak, but it is slightly shifted into different position. Then it is a homogeneously strained lattice strain. Okay, so this is one of the example where they have done SnO2 nanopowder. So they have done with a different hydrothermal condition, and they have given this kind of very nice what is it, analysis. So if you want to know more about this kind of strain due to nano, okay, so you just make a bulk. So this one is a bulk, what 900, and then you make a small nanoparticle. So when you have a nanoparticle, then it will the peak is going to get broadened. Okay, there is no shift, instead there is a broadening of the peak. So this means this is a inhomogeneous strained crystal. Okay, so these kind of things you can also study for when you, in case if you're doing a nano. The same thing can be done on a metallic one. Okay, so if you're having a metal, and if you want to see the strain which is induced in the metal, you can do the same similar kind of things. So these are some of the uses of XRD. Okay, so then there is a big debate whether what is this crystallite size, what is this grain size, what is the particle size. Okay, so this you need to just remember this equation. So crystallite size is always less than or equal to grain size. Okay, and then grain size is always less than or equal to particle size. Okay, so in this case, what happens is, if I take this circle, this is a particle, and if you take this small portion, that is a grain. So in this grain, in this case, grain is equal to the crystallite size. Okay, because both are almost same. But if you take, for example, this one, if I take this is a particle, then what happens? This each thing will be grain. Okay, so you can have more number of grains which are bind together, and then it will form a particle. In the same way, you can have a lot of crystallites. Crystallites means it is a small crystal. Okay, like a polycrystalline. If you take polycrystalline, it is a small crystal. They will just fuse together to form a grain, and then these grains will fuse together to form a particle. Okay, so when we are talking about the crystallite size, we are talking about these small it can be a grain or a crystallite. Okay, not the particle. Okay, particle size is different than the crystallite size. So what you see in case of your TEM or SEM is the particle size, not the crystallite size. So there is a big difference between particle size and crystallite size. Okay, so you need to be very careful when you do this kind of analysis. Okay, so you should not tell, okay, this is a particle size what we get from X-ray diffraction, and then you tell, okay, this is a particle size what I get from temp. Okay. These two are completely different. Okay, what you get from your Scherer formula is crystallite size. Okay, now if you go here, then what are the other contributions apart from your strain and crystallite size? You can also have some contribution due to inhomogeneity in your crystal. Okay, and also some thermal factor. Okay, if you take the X-ray of the sample at high temperature, then what happens? There is the peak would become uh, more linear. Okay, that means it will shrink. Okay, and if you do the same at a low temperature, it may expand. That means it can have something like that. Okay, so those things you need to take care. And then this is your crystallite size broadening. So B 2 theta is equal to K lambda by L cos theta. Okay, so this is a Scherrer formula. So you need to be very careful, especially with respect to your K. Okay, so first thing is when you take the broadening is not just because of the your nanoparticles, it is also due to your instrument. Okay, and when it comes to your K depends on your system. Okay, if you take, so these are the values. So K can vary from 0.92 to 2.08. So you need to know these things. What is the exact value that you are supposed to use for your particular sample? Okay, for case of your NaCl, NaCl is a cubic crystal, and if I am having a NaCl sample, and if my particles are spherical, okay, then I need to use K is equal to 0.94 because it is a cubic symmetry. But if I take the same sample for Fe2O3, Fe2O3 is not cubic. It is a rhomboidal or it is a tetragonal. So in that case, I cannot use 0.94, even though it is a spherical particles. I need to use a different value, which is like 0.89. Okay, 0.89 is the K value for your for Fe2O3. But if I take NaCl, then it will become 0.94. Okay, so these things you need to take care. So there are some, I will share this PPT with you. So if you are working on this kind of nanoparticles, then you need to take care of all these things. Okay. Then how is crystallite size different? So I told already. So you can again go through this. So I'll just skip these things. So then this is one of the things. So when you take if you take your broadening, as I told, the broadening can be due to your size, crystallite size. It can be due to microstrain. It can be due to thermal expansion. It can be due to some other things. Okay. So inhomogeneity in the particles, all those things. Okay. So now how to analyze? If I want to do a very good analysis of crystallite size, then instead of using just the Scherrer formula, so this is your Scherrer formula which you used. So instead of just using a Scherrer formula, you can also use one more equation which is for microstrain broadening. Okay, so this is a equation for microstrain broadening. So B 2 theta refers to full width of maxima. Okay, so I will explain how to get this full width of maxima. So the full width of maxima is given by Scherrer formula for crystallite size. Okay, L is the crystallite size. In the same way, if I take epsilon is the microstrain, then I can also relate the microstrain with respect to broadening. So now, how to use this? The best one is you can go for Williamson-Hall plot, because when you take a Williamson-Hall plot, it will take into consideration both the full width half maximum of your specimen. That means full width half maximum of your sample is the contribution of both your strain and your crystallite size. Okay, so in that case, in that way, you can actually reduce the uh, error in calculating a microstrain or a crystallite size. Okay, so you can use this Scherrer equation. Still, if you want to get better analysis, I would suggest you to better go for this Williamson Hall plot. Okay, so what you're supposed to do is you need to take your data, and then you should make this kind of plots. Okay, so what you have on x-axis is sine theta, and then you have some this is your full width of maximum, which is your B specimen, into cos theta. Okay, so this is almost like you're having a equation like y is equal to just so this is like y is equal to mx, sorry, c plus mx. Okay, c is your intercept, y intercept is this point. Okay, and then mx is your this one. Okay, x is your sine theta, so you can use this is a sine theta. Then this is your x. This entire thing will become your slope. Okay, so this is written something wrong. So 4 times strain is your slope. So if you get this, if you get a slope of this line, then you can get the strain from here. Okay, and then if I want to have the size, then what I need is I need intercept, y intercept. I take this y intercept, then I can use this formula. So y is equal to k. This is, if I call this is c. C is equal to K lambda by size. So I can have size is equal to K lambda by your C. Okay. So this is how you can actually get your strain and your crystallite size from the same plot. So if you want to have more advanced things, I've given this example, one of this example, American Institute of Physics Advances. So there is really good way they have done. So they have taken the same data and they have done different ways of this WH plot. Okay, even in case of WH, there is anisotropic strain model and all those things. So they have done all these things in this on the same data, and they have given a summary of that. And there is one more which is Warren our back method. So this also you can go through. So these are the things that you can go through in your free time. Okay, so then this is what I just wanted to tell. So this is the same thing for if I have a strain, how to get the strain. So I think I'll just skip this, then I will come back. Okay, uh, fine. So this is one of the example I showed in the last case. So when you have this kind of solid solution, you should be very careful, especially I told there is a very good nice shift in the peak. Okay, so this is good when your zirconium is going into the lattice of cerium. Okay, if your cerium is not going into sorry, if your zirconia is not going into your cerium, then what happens? You may get broadening of the peak. This broadening of the peak is not due to change in size. Instead, there may be second phase of your zirconium in this case. Okay, so these kind of things can also appear, so you should be very careful when you do this kind of broadening. So when you're using the broadening to find the strain and also the crystalline size. Okay, so these are some of the things which you need to take care, especially with respect to this. Then I will stop here. This I think I try to go very quick because I want to finish this before I show one more example. Okay, so I will share these things and then you can go through them. So if you are working on nano, you always be careful with this kind of analysis. Okay, when you're doing a when you're using a Scherer formula, don't blindly do some calculation. Okay, because now you know you are already quite well expertised in X-ray analysis, so you should not do the same thing. So someone who may not know, they may do this kind of mistake, but as you already are doing good quite good now good refinement and all those things, you should avoid those kind of analysis. Okay, so now the reason why I showed you these three example is how to get this FWHM. Okay, for example, for your in case of your nano, if it works. Okay, so as I told, your peak broadening is due to your sample. At the same time, it is also due to your instrument. So for getting rid of the instrument, what we do is we take this data for highly crystalline sample. Okay, so now what happened? I have data for high crystalline sample. At the same time, if I open one more, then I can have data for the nano sample, which is my what I have. Okay, so when you take these two data, you need to take in the same instrument and also take with the same parameters. Like if you're using some slits for bulk, if you're using a smaller slits for bulk and if you're using bigger slits for nano, then nano sample, then it's not a good comparison. Okay, you should take with the same instrument parameters, and then what happens, you can do better high-end what is it analysis. Okay, so now how to get this fluid taphmagma? So a lot of people, what they do is they will just take this they import this into the origin and then they just try to fit this. Okay, and then they will say, okay, this is the height, so I will take my height is how much? 3,750. Half of this is something like 1,000. How much? So 3,700. So it should be 1,750, something like that. And then I will say, okay, the peak width is from here to here. So the difference of 33.0 minus 33.31. So it is 33 0.33, something like that. Okay, So that is not correct. The reason is, you can see your background is already at 3000, oh, sorry, 1600. Then your actual height is not 3700, instead it is 2100, right? So then, so these are some of the mistakes normally people do. Okay, so that is why best thing is you just do a profile fit. So this is what we did in the morning. So when you do a profile fit, what you do is, I'll just open this in edit PCR. I will open the Fe203 Nano, which we did right now. So we have done a good profile fit. So now what I do is, I'll go to this output file. Then what I will do, I'll put here in the HKL generation. Okay, HKL, I'll check the first one. Okay, so this means when I run this program, the program has to create this HKL multiplicity, despacing, 2 theta, FWHM, then I observed and I calculated. All these things it has to calculate. Okay, so in a separate file. So I will just do this. This is just a profile fitting. I am not doing a ripple fitting. It is just a profile fitting. So if I just make a crystallographic seq file, it makes no sense. Okay, in this case I am having only, I go to only the reflection file, and then I take the first part. Okay, first one. So now what I will do, I will save this and I will run it. Okay, so now it is doing the fitting. So it is fine. Now I do the same thing for my bulk sample. So I will open the bulk sample PCR. So this is my profile fitting. Then what I will do is, I'll go to output file. I'll go to pattern output patterns. Then again go to HKL reflection. I'll click the first one. Okay, I will check that. Again, I will save it and I will do it again. Okay, so I will just go to run the sample again. Sorry, run the proof again. So it is doing some fitting right now. Okay, so now it is finished. Fine. Now, if I want to do this calculation for generation and all the things, what I can do is what I can do, I will open the file which I sent you. So I think I sent you this file for, so you would have got Excel sheet. So with size and strain. So you open this size and strain your Excel sheet. You can actually create your own. So I just wanted to demonstrate. So I just did this. So here you can see there is a 2 theta sample full width of maximum. Then there is something called as standard FWH. So if you give these things, then what it will do is, your Excel sheet will calculate the D and epsilon. D is your crystallite size from Scherer formula. Then epsilon is the micro strain using this formula. Okay, so the one which I showed in the in this PowerPoint. Okay, so this is independently. You can do the same thing by using a your Williamson all plot. Okay, so that you have to do yourself. So now what I will do is, if I go back to this folder for this, so if I go to this nano, then it would have created something called HKL file. So if I open this in a notepad, okay, for example, so if I open this in a notepad, then you can see these are the information which is there in the in that file. Okay, so what are the things it is telling it as one phase? Then you need this information. Okay, the one which is in the bottom here. Okay, so if you take this, these are some of the things which is written here. So this is your D spacing. Okay, then I think it is not put that. Okay, this is the intensity, and then there is FWHM. So this is the FWHM. Okay, so you can take these FWHM corresponding to the 2 theta. This is the 2 theta, and you have to just copy it to this file. Okay, you copy the 2 theta value corresponding FWHM value. Sorry, I think this one. Okay, so there is something wrong. If you open this, so now, yeah, this is proper. Okay, the previous one was not one with some extension. So don't use this nano one. Instead, you use just nano. Okay, HKL file. There are two HKL files. Use the one without any extension. Okay, then what if you open here, you can see here code means this refers to KL for 1, KL for 2, and then you have HKL. So this is 0, 1, 1, 2 peak. So you don't worry about these things. You have to take this 2 theta value, and you should also consider the full width of maximum. HW is your full width of maximum. FWHM. Okay. So in principle, it is FWHM. It is your software. It will write it as SW. Okay. So then you copy these things for highest peaks, like so, or the peaks with good intensity. Okay. So don't do for all these small peaks. Instead, you take for maybe 5 to 6 intense peaks. Okay. So this is a good intense peak. So you take for this position, and maybe this and this two. Okay. So these are having a better intensity compared to other things. Okay. Don't take the values for this all these small peaks. Instead, you check the intensity. So that also you can get here. Okay. So if you go here, the intensity, you are having 580 is the intensity for the main peak. So you can take this 2 theta value and FWHM into this value. Okay. So I will try to do that. I will copy that, or I will try to write that here. Okay. So I'll keep it like this. So then what I will do is the first intense peak is something like 33.115. Okay, 33.15 is my first intense peak. It has a full width of maximum of 0.205. Sorry, 0.245. Okay. So then I will do the same thing for other one. Like so the next intense is here 470. So you don't take the next one because this is from KL for 2 for the same sample. Okay, so or the for the same peak. So I will do this 35.62. 35.62. Okay. Then what is the full width of maximum? It is 0.2577. Okay. And then you do the same thing for next highest peak. So it is around 2. This I will do for this two. Okay. So this is 49.456, and then the corresponding two is full width is 0.329. In the same way, you can do for the next one, which is your this peak. Okay, 54 point sorry. So 54.06, and then your full width of maximum is 0.3562. Okay, so then you can get rid of other things. I don't have other peaks, so I can get rid of this. So now if I do this even by manually, you will get all these d values. Okay, and if you see here, you can see this full width of maximum should be almost in the same range. Okay, you can ignore the first one, which is for small peaks. If you take from here, it is around 0.24 or 25 to 0.30. Okay, so you should not be too large. Like it should not be like 0.80 then 0.40. That is a big difference. Okay, so normally your full width of maxima should be almost constant. Then you will have very good homogeneous distribution of this crystallite size. If you have bigger variation, even in this case, it's a very large variation. Okay, in this case, what happens? This means my sample is not having very narrow particle size distribution. Instead, there may be a lot of inhomogeneity. Okay, in the size distribution. So that is one thing. And also you can see like for any sample, full width of maximum will increase with respect to 2 theta. This is again due to the fact that this is due to the your instrument contribution. So always try to take peaks which are below 50 degree if you want to do any kind of this kind of particles. Okay. So now I have put the FWHM for my sample. Now what I do is I will do for the same for standard. So what I will do is I'll go back here, then I'll take the bulk, and I will open this bulk. Okay, so I'll open this, and then same thing I get here. Okay, so I get 2 theta value HW full width of maxima. So you can already see that full width half maxima is smaller compared to the sample here, right? So this is almost 0.08, which is almost 3 times lesser than the sample. So this is something good. Like so now what you do is you look for that particular peak. So that is we took for 33.15. So you put 33.15 is already there. So you have to put that value. Okay, 0.0829. Okay, and you can see here this in this case most of your full width of maximum is 0.08. That means it's really good. Like okay, so I can just copy this 0.08 in all the case. Okay, so now whatever you get the d value, so this would be the particle or the crystallite size, and I will put here the average one. So this is already as I told, this is not a very good homogeneous particle distribution. Okay, so it is already having lot of inhomogeneity in terms of particle size distribution. Okay, so these things you need to take care. So at the along with that you get your strain also. So now next what you are supposed to do is you can also do a Williamson Hall plot. What you do is you just take this full width half maximum. You can use this corrected one. Okay, you should always take sample minus standard. That would be your B. Okay, so if I want to do that, I can have this is corrected B. Okay, then I can have this is equal to your sample minus standard. Okay, and then what you do is you just drag it, then it will create some values for FWHM. Okay, so you have values for full width half maxima. Okay, then you need to just have cos theta. Cos theta into full width half maxima will be the your y axis. Okay, just so then you plot that y axis with along with your sin theta. Okay, then you should get a straight line. So you can do this in your origin. You just do you get a lot of points here, and then you find a slope for that. If you find the slope, then you get this kind of uh, analysis what you did. Okay, so this is one this is a better way for finding the your strain and your stress. Okay, and also your crystalline size. So with this I think I will just leave you this all these things with you. So now what I will do is I will just quickly show you how to do for a multiphase, because that is what I'm we are not done till now. So if you have any questions with respect to this, I will take those questions, and then we will go to the next one. Okay, how to calculate Young's modulus and the SSP method? This I think I have to check that, because I even right now I cannot answer this. So this I can explain you again. I will send you that material if you want. So if you have any doubt with respect to this crystallinity, then I can answer. You can ask me questions on this. How can we get the value for K for different samples? So K for different sample you can use for now you can use this table. Okay, so that is why I put this table. So if it is a cubic system like your NaCl or CO2, they are a cubic system. So in that case, if you know the particle that you are trying to form is spherical in shape, then you can use K is equal to 0.94. But in case of iron oxide or TiO2, which are not cubic, which are non-cubic, then you should use if the particles are spherical, then what you can do, you can use this 0.89. Okay, so normally this will not make big difference, but if you are giving this explanation, then your reviewers would appreciate your what is it efforts. Okay, because they know that what you are doing is not something blindly, you are doing much professionally. Okay, so so those things you should know, and there is some I've given some of this reference also. You can go through these references, so you will get more idea on this scale. Okay, so this I have just extracted from here. Okay, so I didn't put myself. This is just copied from this paper. Okay. So if you have any other doubt, if I can answer. If not, what I will do, I'll just show one profile fitting and this one for higher one. Okay. Can we subtract one profile from other from one? That is, when we are calculating crystallite size, we have to compare the profile of silicon and sample. You can do this as long as you can have. So sometimes what happens is, even if I take a TaO2, I cannot have highly crystalline anodized phase, because if I try to heat treat or sinter the TaO2 at a high temperature, then it will change its phase to rutile phase, right? So in that case, I cannot take a highly crystalline sample, right? So for that, what I do is I can use some other sample which is having some peaks at similar position. Okay, so those things you can do in special cases. But for example, in case of my sample, like if I take this sample Fe2O3, this alpha Fe2O3 is the stable form. So I can do just one more sample. I can prepare a sample by sintering the same nanoparticles at a very high temperature, right? So what I did is I took the same nanoparticles, whatever I showed here, the same particles. I put it in a furnace. I made a pellet, okay, and then I put that pellet inside a furnace for 1200 for maybe 4 to 5 hours. Then what happens? I get very highly crystalline sample. Okay, so this you can do, but if you don't have this kind of option, you can go with this kind of whatever is there available. Okay, if you have very good high crystalline silicon, then you take X-ray on this silicon with the same parameters. Okay, if you are taking for 5 minutes with some slits, you should use the same slits for silicon and sample. So those things should be same. Okay, you should not use a very narrow slit for silicon and then broad slits for sample. Then that is not a good comparison. Okay, so you should use the same slits for both the samples. And then in that case, you can just, as you don't have option, then you can do on a silicon sample and then take the X-ray for silicon, X-ray for sample. Then your silicon will become the standard, and then whatever you get for sample, that you can put in this sample column. Okay, so those things you can do, but that is a special case. If you don't have any option, then you can do that. Any other questions? How can we do the strain analysis by using UDM, USDM? Yes, this I think yeah, they are there. Okay, so this is why I put this slide here. So you please go through this, because it's difficult for me to explain everything within this constraint. Okay, so this is just you have the data. You take the data for your sample. You take the data for your standard. Then only thing is the way you get, or the way you arrive at the slope is different. Okay, so if you open this what is it paper, then they have given in detail. Okay, so this is a very good paper. So you can see all these different methods. Okay, so you are doing only one data. You take only one time data, then you have to analyze it. Okay, you have to analyze by using different models. Okay, so those things you can do. So this is little bit you need to spend some time for doing plotting and all those things. Okay, other than that, you don't have to spend much time in taking the data. Okay, so it is the same data. You can, if you have a good data, then you can do all this analysis. Okay, so for this, I think right now I cannot explain everything, because mainly because of time. So I can send you this paper and everything. And if you have any doubt, I am always available for any further discussion. Okay, so you can try on your samples, and if you have any doubt, I can always help you. You can send me an email. I can help you out. Okay. Okay. So I think let us stop at this point with this strain and all those things. Okay. So I think you need to take care of these things when you are doing the nanoparticles, especially crystallite size and the strain. Okay. So when you are talking about that, you can take care of this. And if you do this very well, like as someone asked, if you do all these models, this paper is just based on that model. Okay? They don't have any other things. They have taken one example of some nanoparticles, and they have written entire paper just based on the X-ray analysis, on one single X-ray analysis. Okay, so this is how you can actually give really good what is it explanation. So that is what you should be doing. Okay, so normally instead of just putting some Scherrer formula or something like that, you can go for further analysis. As you know, now you know that you can do so many things. So you can also compare the size which you get from Scherrer formula and strain from this particular equation with what you get in from your Williamson Hall. Okay, you can calculate the crystallized size from purely from your Scherrer formula. Then you do the same analysis by using your Williamson Hall plot, and then you can see what is the difference. Okay, so that is also a good study. Okay, so those things you can do. So let me stop at this point for this, and then I think what I will do is I will just quickly do one multiphase. Okay, so I think there are too many files. I'll get rid of them. So I'll keep this. I will just close this. Okay, so what I will do is I think I had one. I have already done one. I multiphase, so I'll try to look for that. Okay. So I will share you these things later. You can do yourself. So this is the data file. So we will just open this data file by using our collects, and then we'll try to do it. Okay. So this is in different form. Let me convert that into XY form. Okay. So you can also use your wind plotter, for example, to convert the data files. Okay, so if I am having something like that, so this file is having theta 1, theta 2. Sorry, this is your theta starting theta. This is the step and last theta. Okay, and then you have only the intensities. Okay, so now I can actually import that using my wind plotter. Okay, so instead of using x comma y data, I have to just take instrument 0. Okay, so this gives like theta initial, step, and theta final. So that is what we saw there. Okay, so I'll go to that particular folder. I will open this. Okay, some so -4. Okay, so this is with a different -4 with bigger. Okay, let me see. Okay, so this is some kind of data. I will try to just convert this into xy. Okay, so if I want to convert this into xy, what I can do is I can actually go to file, save data as, then you have a lot of other things. So I will just take this save data as xy file, and I don't want to write the header. Okay, and then if you go back into that folder, so if I go back to that folder here, it has written xy file. Okay, so now if I open this, you can see it is in two formats, x and y. uh, you can now use that file for doing further analysis. Okay, you can also do this. So this is actually coming from a different format. So this is a synchrotron data. Okay, so they have done synchrotron X-ray diffraction, and then they get this kind of data. Okay, so this is what they get. So this is a multi-phase. So let us do phase analysis on this first, and then I will show what you get when you do a full probe. Okay, so I will open the QuellX. While doing atomic refinement, which parameters you should and you should not refine. So when you're doing atomic atomic refinement, you should not refine the zero ABC initially. Okay, so when you want to do only atomic refinement, you should do refinement only for scale factor, and then XYZ, that is your atomic positions, and occupancy and BIJ. So those things you can change, but not the not the ABC parameter or your zero parameter. Okay. So once you have some atomic good fit after refining your scale and everything, so final before stopping the refinement, you can always refine ABC parameter and everything. Okay. The reason is if you try to refine ABC when you're doing this atomic refinement, sometimes the peak will completely peak whatever you got with profile fitting will disappear. Okay, so that means it will try to find new position for peak, and then it may collapse. So that is the reason you should not do that. And apart from that, you can do. Okay, a number of background points which like is affects refinement. Yes, it will affect, but also the way you take the your background is also important. Okay, so when you take for example, in this case, for me it will be very hard to find the peak more number of background peaks, because if you see the peaks are very close to each other, right? So in this case, in some cases it will be difficult, so I may not be able to take more peaks. But if it is very flat, then you can take more peaks, so more points, background points. Okay, so that is one thing you should take care. So this again, it depends on the data of your sample. Okay. Okay, so now what I do, I will go for QuellX. Then we will see what are the different phases we have. Okay, so import data. So I have to go to that position. Then I have to take this XY format. Okay, so I cannot do import other things. So when it says for use your wavelength, this is not a copper radiation. Instead, it is a synchrotron radiation. So this I can get it from my PCR file. So I don't remember exactly. So I'll just check it here. So the wavelength is 0.962. Okay, so I will copy this, and then I can put here. Okay, so I'll just paste it. So this is my user defined lambda. Okay, so then now when you do this matching, then it will try to change the wavelength. Okay, so that is why it is important to give the proper wavelength. So now what I do, I just do the background. So I will do it quickly, so I don't want to spend too much time. Then I will do the peak search. So this is too much, so what I will do, I'll just do like this. This is fine. So now if I want to add some more peaks which are missing, I can keep adding like this. Okay, so I can take this and I add these points, which are small peaks. Okay, so these are missing, so I can add them manually. So when you take a synchrotron data, it is only single radiation, not like alpha 1, alpha 2. It will be very it will be monochromatic X-ray. Okay, so monochromatic synchrotron X-ray. So that is why you will not get two peaks. Instead, you will get only one peak for each reflection. So now it is fine. So let us see what are the matches. So I'll just do search match because I don't know what are the phases which are present. So in this case, it will take some time because it will try to match all the things. this is very complicated. I will tell you why. Because if you go here, this is the PCR for your doing Rietveld. Okay. So when you go here, so I have taken the background points. Some of these are the background points which I took. Then you can see there is how many phases. So number of phases, 5 phases. Okay. So it is not a single phase, it is 5 phase. So each phase will have block here. Okay. So JBT0 means it is a full proof. Sorry, it is a Rietveld. And if I put 2, then it will be phase match. Okay. Or profile fitting. So now this first one has 4 atoms. So lead, oxygen, chlorine, and hydrogen. These are the 4 atoms, which is and you have the corresponding XYZ. Okay. So then you have all this information here. So you have ABC values, XYZ, scale is changed. Okay. Then this is the second phase. So this is the second phase, which is your PbCl CO3, and it has 6 atoms. Okay. Then if you go to the next third phase is your lead carbonate, PbCO3. So this is having again 4 atoms. And then ABC, you have the space group of which is orthorhombic space group. Okay. And then you have 2 more phases. Next one is your lead sulfate. Lead sulfate is cubic symmetry, and then it has 2 Pb and S atoms which are in this Wyckoff position. Okay. And then the last one is your calcium sulfate hydroxide. So so this is Wyckoff position and ABC for those things. Okay. This is a monoclinic phase. So one is monoclinic, one is cubic, one is orthorhombic. Okay, this is again different form. Okay, so you have total 5 phases, and if I do the refinement on that, so this is how you do. Okay, you have to add all the phases, and initially you don't have to give this atomic positions. Instead of that, what you do, you just keep JVT is equal to 2, and then you do the profile fit, and then you get the ABC parameters, and then later you can do the retool refinement. Okay. So now let us come here. So as you come here, it has already completed this. So it is showing the first phase is PbOCH. Okay. I will take this is my first phase. Then it will give the second possible phase, which is your Pb lead calcium carbonate. I think next you have I think both are same almost. So when you have more than one phase, it's not easy. Like I cannot finish it in one shot. Okay, so normally you should do slowly, and you should see like it is not repeating. Okay, so they are not repeating. So those things you need to take care. Okay, so then once you have this kind of phases, 5 different phases, then you can go and do the. So this is not a good profile matching. Okay, so if I want to have a good phase match identification, then I should spend some time, and I should look what are the other possibilities like this. Okay, so for this, it is also important to know the history of the sample. What is the history of the sample? What are the elements which are present in the sample? So in this case, it is giving lanthanum, germanium, nickel, all the things. But my sample it is not having any of these germanium, lanthanum. That means this is not a good solution. Okay, so that is why when you're doing with more than one, you should be very careful with respect to what are the possible or what are the possible elements which are present. Okay, you should know those things, only then you can do that. Okay, so I'll just show how it looks. So for example, this one so I will just open the final PRF file for how it looks. Okay, so this is how it looks for when you once you complete your retool refinement. So this is a very challenging, because you cannot just I cannot show it in just 30 minutes or 1 hour. Okay, so it needs very patience to do one by one. So maybe I will show one with some other sample with 2 or 3 phases. but if I want to do, you can do also for 5 phases. Okay, so this is the fitting I did for this sample. I can run it one time if you want. So let me do only 2 cycles, and then if you put RPA as -1, then what it will do, it will create the zip file. Okay, it is similar to opening this file PCR in your EDPCR and clicking the zip file. Okay, checking the zip file. So this is the same thing. So I'll just try to run that. So when you are having so many phases, sometimes it's not easy to get low chi-square, because this chi-square is weighted from all the phases. So some phase may be having very good fit, some may not be having good fit. Okay, so in that case, you may not come up to less than 3. Okay, but it is acceptable, especially when you have a multi-phase like this. Okay, so now if you see, this is a fit that we got for 5 phase. And if I want to open the crystal structure, what I can do is I can go here, again use the Vesta. And if I want to know the fitting, what are the fitting things, so I'll just show this before going to crystal structure. So you try to open the out file and also some file. Okay, so I will open this out file, which just it has again updated. And if you go down, you will get information about the phases here. Okay, what are the phases which are present, and it will also give what are the fractions. Okay, so this is one. The first phase is having like something like 37.6%. The second phase is having it is 17.8%, around almost 18. Next is 21%, then 5%, and 18%. Okay, so now if you add up all the things, it should come up to 100. So this is how you can also get the weight fraction or the distribution of each phase in your sample. So these are the different phases which you have. So you can know the number of or the weight percentage of each phases. For example, if you have a mixing of your anatase and rutile, then you can know what is the contribution of anatase and how much is the quantity which is rutile is present in a given sample. Okay, so this is one thing which you can do with multiphase. Okay, so when you have multiphase, and then apart from that, you can do other things also, like crystallite size, all those things. So then I will show how to plot. So for Vesta, what you do is you again select a new structure, then you delete this whatever is present here and try to import. Okay, so import the uh, zip file. Okay, so zip file is, I think, this one. Yes, so this one I import. So you can see here it is giving different phases. Okay, so I will just say okay. So now if you want to see, right now you are seeing the laurinite. Okay, so if you go back, you can see here there are different phases. Okay, so if you go to this object, then you can see there is gypsum. Okay, so if you want to see gypsum how it looks, then this is the gypsum. Then you can have all these phases. So you can toggle between each phases. Okay, so you can this is how you can get crystal structure for most of your phases. Okay, so this is one thing, and then I think I will try to do one uh, okay. So I think I gave some multi-phase also with one of your in one of your email. So let me check. I think you should check this. Okay, so there is a file called this D5052, something like that. So if you open this, this is a multi-phase. Okay, so I will just try to show how to do a profile match for this. So before we can stop this workshop, okay? So this is the same thing. So when you do this, first we should know what are the phases. So I will go here, I will take a new file and I will try to import that file, okay? So you can import any file, both are X file. So this is with the copper K alpha. I will do the background. I will do quick search. So I think it's fine because it has taken most of the sample peaks. Then you can just do search match, okay? So now you can see this is telling, oh, so it has some part is Y203. I will click OK, this is my Y203. Then it will give the second page is W03. Okay, so you can see it is putting for missing positions. So still there are some peaks which are not identified, so it's fine. I will take this. Then it is showing the next phase is silicon. Okay, so I know my this data is from a sample which is having 3 phases. So this is what you should know. Like you should know what are the compositions which can be present here. Okay, so then you can get this starting one, and then what you do is you can take each phase and then you can start plugging into uh, your PCR file. Okay, so this is what I did yesterday. So I'll just open this file. Uh, so I have sent this file. Along with that file, I think there is some other files, data files, which also already give you the information. Okay, so if you open this, along with that, there is a Word document which is already giving the what are the phases which are present, or what are the possible elements which are present. And then I have also given this crystallographic SIF files, so you can get atomic positions for each of these phases. Okay, so this is a multi-phase refinement that you can try. And then I have given these details. Okay, what are the things which are there? Okay, so it says, okay, it has 3 phases: Y203, W03, and silicon. Okay, so now using that information, you create a PCR file, and this PCR file. So I will show this phase, multi-phase. So this file, you enter all the information that is necessary for pattern. So this is X-ray pattern, and then you select the X-ray data, multi-phase. Try to save that as .dat. Okay. So if not, if you save it as .xy, sometimes it is not going to work. Okay. So that is one thing you need to take care. Then rest of things are already well explained. Then what you do is you go to phases. Then you can see here I put 3 phase. So this is the first phase, which is Y203. Then there is a second phase which is W03, and then last there is one more which is the silicon. Okay, so then you can just do refinement only for profile, and then you introduce the atoms later. Okay, so one by one you can do. You don't have to do all at once. You can do first only for Y203, then you do for the other one. Okay, so let me just do that. Maybe I will try. uh, so I will just put Y203, and then pattern is I'll add the pattern, then I'll use the pattern as the data file. Then this is your X-ray with K alpha 1 alpha 2 Thomson exclude. Background is linear. Then excluded region I will just leave it. I don't want to do anything. Then I will save it with a new name. Okay, so I will just put a new dot PCR. Then I will take first phase. I will tell this is a profile matching. I don't want to do right now this one, so I will tell this is Y203. Okay, so then what I do is I have to go give the contribution. Contribution is this is X-ray, and then shape I will take it as Thompson, and then so symmetry, for symmetry I have to go to the file. Okay, so I'll just open that file, PCR. So symmetry in this case it is 14. 14 means I put the number instead of putting the complete this one. So I'll just keep 14 is a monoclinic. Then I save it, go to refinement, and then I try to import those data. I had done this data yesterday. Let me check again. Okay, fine. So it is in the right folder, so it's fine. So instrument, I'll make it as this is one. Then in the profile, I have to put these ABC values. Okay. So when you want to put these ABC values, make sure. Oh, sorry, I think I put wrong. So for Y203 it is 206. Okay, I have to change it. Okay, fine. First, I will copy these values. Then I will again go back and change the Facebook. So this is a cubic. All will be same. You have 90, 90, 90. Okay. So this is fine with the this part. So what I will do, I would better open it in Notepad, so it will be easy for me. Multiphase. So this is one which we created. I'm going to copy it here, and then I'll make this as auto as 1. Number of cycles I'll put 10. Then I need to change the this to 206. Okay, so 206. I'll save it. So then I will ask the program to run 0, and also I will ask the program to run the ABC. Okay, so this is 1, then this is 2. A is equal to B is equal to C, so it is 21, 21, 21. Okay, if it is different, then you need to give different values. Okay, fine. So now what I will do is I will just run this program. So you can see it is not taking all the peaks. Instead, it is taking only few peaks because it is trying to index only the peak which are coming from your Y203. Okay. So these peaks are coming only from Y203. So rest are left like that. Okay. So it is not trying to take them into account. Okay. So there now we will go and introduce the second one. Okay. So for just to do this, what I can do is I will copy all this information, okay, and then I'll just put it here in the next line. So this is your second phase. So you need to change it as 2 phases because I did only 1 phase. Now number of phases 2. Then you you can always try to copy this WO3. Okay, so WO3 ABC I will copy. Okay, copy this entire ABC, and your space group is 14. Okay, so I will go here. In the second one, I will call this is a WO3. Okay, so this is WO3, and then this is space group is 14. So accordingly, this is a monoclinic, so I have to change these ABC values, alpha, beta, gamma. So these are the starting values. So as I have used 1 and 2, I have to change this to 3. This is 4. This is 5, and also beta will be 6. Okay, so this is 5. Beta will also change, so I'll just keep 60. Then I need to generate HTL for the second phase. First phase it is already sitting in the folder. So if I go back, it will be there with the new. Okay, so if you see here, HKL would be there already for the first phase, but you will not have for the second phase. So for that, I need to generate it. Okay, so I will put this as 0. If I put 0, that means it is to generate from the beginning. So now I will go and run that same PCR, new PCR. So now it has started taking some other peaks. Okay, so that is the sign that you're having your second phase. Okay, so now if you go, you can see it is already taking some points, but it may not be exactly taking all the points because, for example, this is missing. So here it has taken almost all the peaks, but at some point this is a big peak. It's not a small peak. So in this case, you need to take into account the third phase. So what I will do is I'll put the third phase. So I'll go here, I'll make it as 3. I'll do the same thing. So I just copy it, the first, this part, only this part. I am going to paste it here, and I'm going to call this is the third phase. So this is the third phase is actually your silicon. So 227 is it is again a cubic system. So I'll go here, I'll call this as silicon, and then this is 227. So this is 227. Save it. We change this ABC value again, and then so I stopped at 6. Then I have to start here at 7. Okay. So everything is 71, 71, 71 because it is a cubic system. Okay. Then you don't have to worry about it. Alpha, beta, gamma, they are already 90°. So now if I run this, then this peak has to be taken into account. Okay. So let us see if it works or not. Okay. So you can see here it is giving error that there is no new 3.hk. That means I didn't make this 0. Okay. So if I don't give it 0, then it will look for some HKL file. So if I refresh this, so you can see previously it was only one HKL. Now there is two HKL. Okay, so the one is from first phase, two is from second phase. So it was also looking for the third phase, which we don't have. So it will stop. So what I will do is I will again start by putting 0 for this one. Okay, IRF for the third phase is 0. Now it will generate new HKL files. Okay. So now it is running, and you can see it is already coming down. Okay, so your chi-square is coming down. So you can run it again. So till you get a good, reliably good fit. Okay, so now you can see it is not changing much. Okay, so 19.3, 19.6 is toggling. So what you can do, you can refine the your x and y parameters. Okay, so this is how you can keep continuing the refinement for more than one phase. Okay, so this is for profile fitting. Now what you do, you save the same data as atoms, and you can introduce the atoms in your file. Okay, so this again it is already given in your the atomic positions are given in the zip file. So you can open this zip file for silicon, then you get atomic information for your silicon. So silicon it is in 8A, only one this one 000. Okay, so your Wyckoff position will be 000. In the same way, if you open your WO3, which is monoclinic, I think you can have more peaks or more atoms. Okay, so if you see here, you have to copy all this information. Okay, so there are two for tungsten, then maybe 6 oxygen, okay, because this is a monoclinic, which is less lower symmetry, and then in that case you will have more atoms in a unit cell, okay. So these things you need to copy into your in your PCR, and then you can run, okay. So this with this I think I will stop here, because we are almost there, and if you have any more doubt you can always write to me. So before I stop, you have to I will send you the link for your feedback. So fill the feedback form, and also try to fill your quiz and assignment. So when you are filling your feedback form, you please type your name properly, so that the same thing will be used in your certificate, okay. So for generating the certificate, we are going to use those information. So we need your information about your I think I'll just check what are the things. So so for your certificate, we need your name along with your title, okay. So if you want, if you are already a PhD holder, you can put a doctor, okay. Then we need your designation, like if you want a research scholar, you put a research scholar, and then we need your institute, okay. So affiliation, so you can put this affiliation with your place and the country, okay. So you can also include your place and country in your affiliation. So these things you need to put properly in the feedback form. So though the same thing will be used to generate this certificate, okay. So please do that when you get the feedback form, and then you have to give some 1 week time to generate all the certificate, okay. It will take some time, but you will get the certificate for your this one, okay. So after in your email, so then before I start, I think for stop so the indexing, I will again give you a step-by-step process. So XRD, as you know, like it can be used for several applications. So for nanocomposites, polymers, material science. So these things, whatever you learned, I think it will be useful for most of you in the entire spectrum of these fields. Okay. So with that, I think this is what you. This is the present scenario. So you have almost reached the destination, but still what you are supposed to do is you need to practice all the things what we have learned in last 4 days, okay. If you don't practice, then it is very difficult to get a grip on this. So if you practice more, then you get more grip on this, and I think you can use that for your research very well, okay. So with that, I think I will also like to again thank. So this I did it in the first slide. I again want to do it because we are using all these foolproof ESTA which are free of cost. Anyone can download and everything and use it, and it is mainly because of contribution from all these people from ILL, okay, Institute Laval Angevin. This is in Grenoble, France. So they are developing these foolproof and VESA programs. So similarly, there are so many other free softwares, and there are also very good, nice reading PPTs from which you can download from different places. So for even for my PPT, to make my PPT, I have used different resources. So I like to acknowledge them. So also before I stop, I think uh, just so before I stop, I want to thank our director, M.N. Chirikosappa Shivakumaraya, who is our CEO, and also our principal, KP Shivananda. So they are very much encouraging in doing all these kind of uh, workshops. So it was very good to have their support. And also we have a lot of support from our department also. So our HOD Suresh sir, I think he is going to do again validation, and then other faculties Bhargavi, Sridhar, Manor, and Manjunath, along with supporting staff. So everyone has helped us to do this workshop very well. Okay, so then I think With this, I will stop this, and then I will hand over my control to Suresh sir, who is our HOD. So he will give the validation. Okay. Okay.
Uh, Dear participants, very good afternoon to all of you. So now we are coming to the end of the program. It is my humble and devotional pranams at the lotus feet of His Holiness Dr. Sri Sri Shivkumara Swamigalu, founder president of Sri Siddhganga Math, and also Sri Sri Siddharanga Swamigalu, the president of Sri Siddhganga Math, so who have blessed us in successful completion of the 4-day international workshop on X-ray diffraction. Dear friends, as you all know that a lot of research work is going on in and around the world in searching of functionalized materials with potential applications in science and technology. Before subjecting to them for the applications, the materials need to be characterized. Among them, XRD analysis is one of the best and versatile tool among others. So with this intention, the physics department has conducted the hands-on training on XRD analysis using the available free software. Of course, this is our second workshop conducting on this XRD analysis. So first one was conducted during the year 2018. In that, more than 50 participants were attended. And this time, around 100 participants, including foreign scholars, are participated in this online workshop. Now I request a few of the participants to share their views about this workshop because your feedbacks are essential to review ourselves. So dear participants, please raise your hands or unmute your audio and video yourself and can share your views. Dear participants, kindly I request few of you to share your views about the workshop. Am I audible? Hello? Dear participants?
Yes, sir. Sir, this is Tejas. Hello.
Sir, please.
This is Tejas from Presidency University. I'm a research scholar in the
Oh.
Presidency University. And
Okay.
thank you for giving this opportunity to learn about the refill refinement, about the 4-day workshop. And I learned many softwares and the very programs for the refill refinement, doing the XRD analysis of the everything about the XRD analysis. The Madhu sir has given explained us in a very beautiful manner, and also he explained a step-by-step processes, and everything he is repeating us for that. And also the mails which are sending by the mothers are daily updates and everything, every videos which we can you are updating in the YouTube, and we can repeatedly watch it. And if I cannot understand means
Yes.
I can able to watch and every at a time. If I miss something means I cannot able to recollect it, but also I can watch in the online also.
Online videos. Yes.
Yes, for that, thank you so much for organizing this one because it's very, I thought that it was a very difficult to the refinement, but now it's very easy thing.
Yes,
And now
yes,
it can
yes.
be easy for my single phase analysis of my PhD things and all. Thank you so much, sir. Thank you for the organizers and all. Thank you.
Thank you. Thank you.
Thank you, sir.
Thank you for sharing your views. Next, anyone else? Shall Ismail, could you share? Yes, few of you can share your views.
Hello.
Ah, yes.
Afternoon, sir. This is Kapil here from Bhopal.
Please tell me, sir.
That the workshop is very good and explanation is also very excellent.
Thank you, sir.
Everything is good, but for the fresher
Yeah, yeah.
who are beginners to this is little bit confusing because they don't know from where it is
Yes, yes.
starting. But who knows a little bit of Rietveld, for them it is very knowledgeable.
Okay.
Yes, sir. Thank you for this, sir. We gain a lot of from this.
Thank you, Kapil Dev. Thank you for sharing your views.
Thank you.
Next, anyone else? Don't hesitate because your feedback makes us to learn if any shortcomings in organizing this workshop. So we need to know your feedback.
Sir, one more word I can add this one.
Yes,
The
go ahead.
workshop.
Oh,
Yes, as
yes,
Kapil
yes,
sir
please.
said that, yes, Kapil sir said that we are the beginners,
Yeah.
and also we want to share that this is the short term, you have completed everything. Sir, because for that, I have completed by one 200-page notebook because while writing and while scribbling these things and all. As we know that because here we cannot able to do the multi-peak fitting and all.
Okay.
For that purpose, I'm requesting you, sir, for the Madhu sir and the faculties, please help everyone for the multi-peak fitting for us for that purpose, sir.
Okay, sir.
Because a multi-peak fitting is very difficult for us.
Mhm.
And also, Kapil sir, here we can find in the online every zip file is available. In that zip file also, I gone through the zip files and all. In the zip files, many information is available, and we go through that. We can easy to correlate with our results and also the which are resulted present in the online. Thank you, sir. Over to you, sir.
Thank you, Tejas. Thank you. Anyone else would like to share? Okay. So I hope this workshop would have satisfied your expectation. So if that is the true case, then the entire credit should go to Dr. Madhu Channabasappa because he conducted this workshop in well-organized manner and also all sessions were conducted in time. I hope he explained all your doubts during the sessions as and when you rise. Still, if you have any doubts or if you need any help, you can contact him at any time. Without any second thoughts, I am assure you, he will help you. So if you find any shortfalls during this workshop, please excuse us. So your feedback or suggestions definitely help us to improve ourselves in organizing the conferences or workshops in future. I'm very much thankful to our CEO, Dr. Shukumar sir, who has encouraged and helped in all respects in organizing this workshop. I seek his guidance and support in future also. So thank you very much, sir. Also, my sincere thanks to our principal, Dr. K.P. Shivananda sir, for his support in organizing this workshop. I am thankful to all my colleagues for their cooperation during this workshop. Finally, on behalf all of you and on behalf, I am congratulating Dr. Madhusi for successfully organizing this wonderful international workshop and also as a resource person. So before I conclude, I pray the God to keep all of us with good health from this COVID-19 pandemic. In this situation, we all should maintain social distance and use masks to stay safe and healthy and happily. Thank you one and all and wishing you all the best. Now over to Madhu for announcements, if any, to the participants. Thank you one and all.
Thank you, sir. So if you still have any doubts and anything like that, you can always write back to me. And also try to submit your quiz and your assignment so that I will know how much you got it actually. So it is not to judge how good you can get the scores. Doesn't matter. It is just only just way of having your assignment. Okay, and also I will send you the feedback. So you try to fill it out. And also for multi-phase, I will make a video and I will send you. So because I think it was a little bit difficult. So I tried to cover that, but I know like it was too quick. So I will try to do that again and then I will send you. So thank you one and all for your wonderful participation. I was very happy because we didn't add any moderator or anything for this in this case. So still it was easy for me to actually uh, conduct myself because I don't have to um ask anyone to mute or unmute or anything. So even with 100 participants, it was very smooth way, and it was mainly because of your kind cooperation. So I think I'm very much happy for that, and I thank you one and all. So I hope you use this and use this information in your research, and I hope you get you can target better and also high impact journals. Okay, so even if you have any doubts, especially when you're doing your own sample analysis, you feel free to write to me. So I will help you out. It's not a problem. So right now you have very basic knowledge. So I didn't want to put too much again about that. So that is why I'm stopping at this point. But still, you can do a lot of things with ritual refinement. Okay, so that we can you can learn one by one. So try to what I request is you try to practice these things, whatever you learn. So now I think you have a lot of resource. So only thing is you need to put lot of time on this. So most of you are maybe in still quarantine. Maybe your classes are not started. So this is good time for you to practice these things. So please utilize these things, and then uh, if you can get something some betterment in your research, then that is a big that is a real success of this workshop. Okay, So that is what I believe. And also I try to use only the free software because then it can reach more people. If I use some software which are commercial, then it's not a good one, because we know like it's very difficult to even get funding for instruments. Then we cannot expect funding for software, right? So that is one of my aim. So I don't want like even for, even a research scholar, it will be difficult to spend money on a software. And if you see the money, it's not very small, it's quite a, big amount. So that is one reason I try to do this. So but you can choose your own software. I don't say you have to stick with the full proof. So that is your wish. So whatever software you want, you can choose. So with this, I think, and if you still have something, you can always write to me. So you have my email and everything. With this, if you don't have anything, we can stop. So thank you very much, and have a safe stay with this management. So hope to see more interactions in future. Okay. So thank you very much. So we'll stop at this point, and then maybe in future we'll have again. Okay, we'll meet again. Okay. Thank you.